All right, this is the first of a series of videos. We are on Unit 9. This is the last unit of AP Chemistry. And it's divided into two parts. The first is going to be a continuation of thermodynamic or thermochemistry, a little bit more detail, some new concepts for you, including entropy and Gibbs free energy. And then we're going to wrap up the unit with electrochemistry, which partners really well with thermodynamics. So those are our last two subjects, and then that will take us into about a week and a half long review before the AP testing week begins. Okay, now for us in Zoomdal, this is actually chapter 17. And remember when we looked at chapter 6, which is the thermodynamics chapter, we talked mainly about enthalpy. It was about energy. And remember that we learned about the first law of thermodynamics, and that states that energy is conserved, right? It cannot be created nor destroyed, but it can be transferred from one form to another. So I can go from heat energy to kinetic energy, that way. So it's conserved, but it can also be converted, I should say, from one form to another. Now, we briefly talked about the definition of what's called internal energy. You are not required to memorize this equation, but it does tell you what are the two components of the internal energy of a system, and that's heat and work. Now we are going to focus primarily on the work aspect of this. We're going to look at how heat energy is absorbed or released by the system. In fact, all of our thermochemistry that we did before was about enthalpy. We're going to add two components to that. And we're going to start looking at how internal energy affects whether a reaction will or will not occur. Now, the way that is described in chemistry is spontaneity. So a spontaneous reaction is one that proceeds on its own without any outside assistance. So I'm not heating it, I'm not putting in an electric current, I'm not doing anything under the conditions that I'm studying. I'm leaving it, and it will either occur or not occur. A spontaneous reaction, if it's reversible, occurs in only one direction, because if it's spontaneous in one direction, then it has to be non-spontaneous in the other direction. All right, so let's kind of look at what this means. Let's look at some examples. So I've got a phase change here. I'm going from a liquid to a solid, but it's at 10 degrees. Now we know that water freezes at 0 degrees. So at 10 degrees, no problem. This is going to be spontaneous. So one thing I want you to note here from here on out, you are going to have to watch your conditions. By that I mean, when you start talking about the spontaneity of reactions or whether they will or will not occur, you need to look at temperature and pressure. Because although this is spontaneous at minus 10 degrees, it would not be spontaneous at 100 degrees. What about the gas flowing from A to, or it says here, the gas B moving completely, the whole thing, from flask B to A? That is not going to happen. Now, I am going to get some mixing of these gases, but we are not going to exchange places. Statistically, that is just not going to happen, so therefore it's non-spontaneous. All right, let's look at this reaction. Water going to hydrogen and oxygen at 25 degrees C and 1 atmosphere. Well, we all know from personal experience more than likely that this is not spontaneous, but I want to preface this by saying that just because we can't see something happen or it happens really slowly doesn't mean it's not spontaneous, and we'll get back to that in a minute. But I need an electric current in order for this to happen. This is the only way that I'm going to break this apart is with an electric current. So that's an input. Therefore, it is not spontaneous unless assisted. What about this one? This is just salt being thrown in water, 1 liter at 25 degrees. This is spontaneous. Usually, dissolving is a spontaneous process. I don't need to provide any assistance to do it. You throw it in the beaker, it dissolves. Let's look at this one. A liquid going to a gas at 100 degrees. We're going to call this spontaneous. I am right on the edge, right? Because I'm right at 100 degrees. But at 100 degrees, I should be able to go from a liquid to a gas at 1 atmosphere or standard conditions. Okay. Now, why is this ambiguous? If a pure solid is at its normal melting point or pure liquid is at its boiling point, there's no preferred direction for the process because they're in a state of equilibrium. So remember, if we think about our heating and cooling curve, so if I have this, when I'm at the plateau, I have this mixture, the energy staying the same, right? The temperature is not changing. And so I'm at this equilibrium where I have this mixture of each phase at these plateaus. And so it's spontaneous, but it could go in either direction. Now, remember that ice melts greater than 0 degrees and water freezes at temperatures less than 0 degrees. So spontaneity can be temperature dependent. Because if I want to say, is the ice going to melt at 25 degrees C? Yes, it will be spontaneous, but at minus 10, it is not. Now, it is important to understand that just because, this is super important, and I'm going to underline this. It is important to understand just because a process is thermodynamically favored does not mean it will occur at an appreciable rate. That means it could be really, really slow, but I still do not need to assist it. One perfect example of that is the formation of iron oxide or rust. If I put the metal outside, leave it on my back porch, unprotected, iron will rust over time. It just takes a lot of time to do it, but it is still considered a spontaneous process. All right. Now, although a majority of spontaneous reactions are exothermic, there are some spontaneous endothermic processes. 2 examples are melting of ice at room temperature. Remember, I'm at room temperature, which is about 25 degrees C, and ice melts at 0. And the dissolution or the dissolving, solution, I think that's 1L, of solid ammonium nitrate, in which was mentioned in our textbook. I think you'll also see this in Zumdahl. When I dissolve ammonium nitrate, simply dissolve it in water, it is one of the few salts. Most salts do not absorb energy when they dissolving, but ammonium nitrate does, and it is an endothermic process that is, because it is dissolving, is considered to be spontaneous. A non-spontaneous process can occur only if the surroundings do work on the system, not me. So the temperature of the system, maybe the pressure of the system, will cause a non-spontaneous process can occur only if the surroundings do work on the system. That means I have to heat it or apply pressure to it or something that implies assistance in order for that to occur. Okay, so that's kind of a definition that in the chemical nature, there are some reactions that will occur under certain conditions unassisted and some that will not. Now, what we're going to look at now is a series of 2 new concepts we're going to combine with enthalpy to evaluate the spontaneity of a reaction or whether a reaction is going to occur. This is really important information because if I am designing a chemical system that I want to work for me, then I need to know what I may or may not have to do in order for that reaction to occur. So in a chemical plant, for instance, if I want to make a particular commodity, it's going to be a lot more profitable to me if it is a spontaneous reaction, let's say it occurs unassisted, than if it is a non-spontaneous one where I might have to apply heat or pressure or something like that. Okay, now the first concept that we want to look at, which will be combined with enthalpy to determine spontaneity, is what's called entropy. Now, entropy is a word that is associated with the extent of randomness in a system or disorder. And you might think, well, that's a weird concept. It's really a physical concept, but it follows kind of what nature tends to do, right? Order requires energy. Randomness does not. And so it tends to be that energy, an increase in energy, it can be associated with, to the extent in which energy is distributed among the various motions of the molecules of the system. And so randomness in and of itself, am I going to a more random system or a more ordered system which requires more energy in the reaction system that I'm looking at? Entropy will be a factor in determining spontaneity. Now, delta H, we've already talked about, refers to the change in enthalpy, and delta H refers to the change in entropy. Okay, so how are these going to work together? Now, I'm going to this is right from the AP Chemistry course exam description, and so I'm going to kind of highlight the concepts that you need to know about entropy. Now, we're going to really look at entropy qualitatively. We're going to use the numerical value to look at the Gibbs free energy, but in and of itself, we are going to just use it qualitatively, and we're going to use it to make predictions about the direction of the entropy change for typical chemical reactions and reaction processes. Where we started, where we end up. Now, entropy increases when matter is dispersed. That is the tendency of nature. Nature tends to go towards disorder or randomness. So a phase change is one. From a solid to a liquid or liquid to a gas results in a dispersal of matter in the sense that the particles become more free to move. Another way in which entropy increases in this context is when the number of individual particles increases when a chemical reaction occurs. Maybe I go, in the case of a decomposition reaction, from 2 particles to 1. That would be a decrease in entropy. Or a synthesis reaction where I would go from a synthesis reaction would be 2 particles to 1. That might be a decrease in entropy. But a decomposition reaction where I go from 1 particle to 2 would be an increase in entropy. Also, for a gas, the entropy increases when there's an increase in volume. Or you could say that the increase in volume indicates that there is an increase in entropy. And the gas molecules are able to move within a larger space. So it's increase in disorder, increase in randomness. Energy also increases when energy is dispersed, right? So from kinetical and molecular theory, we talked about how kinetic energy is distributed among particles, and we drew the Maxwell-Boltzmann curve, which we're going to see in a minute. And as you change the amount of energy that you have dispersed, where more particles have more energy, your entropy is increasing. Therefore, as the temperature increases, the entropy increases too. All right, so let's kind of put all this together. We're going to look at what we know about enthalpy and what we know about entropy. We're going to put the two together, and we're going to start examining some chemical reactions.